Welcome, and in case you don't know us yet, we are Mission Critical Energy, and we know remote. We have helped keep sites located in harsh and extreme conditions up and running for over 20 years. Our projects have reached around the world, from the near Arctic plains of Nunavut, Canada, to the open oceans of the Atlantic and Pacific, the North Asian steppes, down to the New Zealand highlands. Places where power alone is not the priority. It is about the people and the need, and that is where our knowledge and experience allows sustainability to be part of the goal. As off-grid professionals, we know how important it is to listen to our customers and develop strategies and equipment that can benefit everyone. One of these important assets has been the Mission Critical Energy autonomous remote switch for micro wind turbines, the first of its kind in the world. So why is such a simple-looking device so important? Well, the science behind even some of the best micro-wind turbines in the world is starting to demonstrate that the turbines can survive in extremely high winds when they are in the stopped condition, or as some would say, off. In remote places around the world, survival is just as important as the electricity these turbines provide. For instance, the SuperWind 350 micro-wind turbine can safely operate in the run position, making power and charging batteries up until about 80 miles per hour. However, when in the stop or off position, the turbine is likely to survive in winds above 100 miles per hour, with an upper threshold of 110 miles per hour. This is an important consideration when using a micro-wind turbine as an off-grid power charging resource. At most sites, wind speeds are below 75 miles per hour most of the time, but worldwide shifts in weather patterns in the past decades are trending toward storms of higher intensities and of longer durations, threatening micro-wind turbine health. The survival of a micro-wind turbine during these events typically means the survival of the off-grid site, so it is very important to understand the basics of micro-wind turbine survival. Most DC output micro-wind turbines rely on dynamic braking to survive when turned off. Simply put, this is the near instantaneous disconnection of the wind turbine from the charge controller and the batteries, and then the immediate connection of the positive and negative wind turbine output wires. To many, this would appear to be a short in the system, and that is correct. Yet the science would also say that dynamic braking is a proven method of small wind turbine control that involves actually short-circuiting the generator stator windings. And this short circuit results in a large back torque force. The magnitude of that force depends on rotation speed and configuration of the generator. This is considered a safe practice in well-designed and correctly installed microturbine systems. Since a mechanical braking system is neither feasible nor cost-effective in a micro-wind turbine use, dynamic braking is the only professional solution to turn off a micro-wind turbine. Although it is an industry standard, dynamic braking also has a disadvantage. It can never force the wind turbine to stop completely, meaning the rotational speed can be reduced without involving a mechanical brake, but only if dynamic braking is activated before wind speeds become too high for the strategy to be foiled by physical forces beyond the capabilities of dynamic braking. So, to be safe, a turbine needs to be off or stopped with dynamic braking before the most extreme winds occur, or there is little hope of saving it. Historically, dynamic braking was achieved by way of a simple, four-way manual on and off switch. In the following order of run to stop, the switch would safely disconnect an operational wind turbine from the charge controller and batteries. Within a millisecond or so, it would short the output leads from the turbine, hence shorting the stator windings, enabling dynamic braking to commence. Stop to run was a reversal of the switch, and these same actions including the important timing between connections. If timing was not exact, the result could be a battery-based short, resulting in a large electrical arc and potentially damaging heat, a runaway turbine, or both. For hobby-type equipment, this can often result in damage to the equipment as well as the battery bank itself. For professional equipment such as the SuperWind, a turbine needs to be in a loaded condition while in operation, or off via dynamic braking. This means the wind generator is connected to a powered and complete circuit, not an open circuit. and in this sense, dynamic braking also loads the turbine in a closed-circuit condition. However, batteries are not being charged, and the generator's electrons can only flow through the stator, and the wiring ran to and through the stop-run switch that is completing the intentional wind turbine stator short while in the stop position. If a turbine is allowed to spin without being connected to a complete circuit, it is called an unloaded wind turbine. This is a very dangerous condition, as it can spin far faster than designed, leading to very high voltage potentials, all the while building serious centrifugal forces that could rip it apart, even in winds that would be within its operating range if it was loaded. For wind turbine users, this information is critical to long-term success and planning. So with the characteristics of starting and stopping, or as one may say, controlling a micro-wind turbine, a paradox quickly arises. Micro-wind turbines are a great source of power for remote sites in harsh and extreme conditions, but these sites are also very difficult to reach. So what good is a manual on-off switch if one cannot reach the switch when needed? First, the manual on-off switch is a must during installation of the wind turbine and during inspections of the wind turbine, as the operator can physically turn the unit off. This allows them to make sure no electricity is flowing to the batteries and allowing the blades to slow down to a crawl in most conditions. This is also important during repair work or when batteries need to be replaced. But when considering that most of these sites are remote and some are only reachable seasonally, how does one stop a micro-wind turbine without being at the site? Survival of the turbine and perhaps the site operations are now at stake after all. The answer comes after a decade of development and testing, the Mission Critical Energy Autonomous Remote Switch, or ARS for short. In the past 10 years, there have been many off-grid remote monitoring systems available, including some with an optional dry contact or a remote control on-off contact that can activate other devices. Mission Critical Energy's first ARS was able to work with these devices. This allowed the owner to manually adjust remotely and turn the dynamic braking feature on or off on a small DC output micro-wind turbine without having to go to the actual site. This includes the SuperWind 350 turbine. In 2020, we took our ARS technology to the next level and produced the MCET-ARS system, a single ARS switch available for 24-volt or 48-volt off-grid systems and designed for end users with supervisory control and data acquisition or SCADA capabilities. This includes the FlexSCADA Q5 or the FlexSCADA Q5 Pro at their remote sites. With the capabilities of the FlexSCADA technology at a site, the MCE-ARS would allow activation of the dry contact based on the operator's need manually. This is done by automated triggers or even date or time settings, turning the wind turbine off during summer or bird nesting season, for instance. With the addition of an anemometer or anemometer trisonic mini weather station, the SCADA system can automatically shut down the turbine at 70 miles per hour while also greatly improving the turbine's survival in winds above 100 miles per hour. The FlexSCADA plus ARS plus wind sensor system strategy allows the turbine to automatically restart once winds have decreased to an acceptable preset level by continuously monitoring wind speeds, as all the while the operator is sent special messages on the status of the wind turbine as well as the health of the batteries and other systems at the site, monitoring by the FlexSCADA. The newest MCE-ARS switch also has current sensing built right into the switch, so turbine output can be directly monitored into a FlexSCADA type device without the need for additional amp coil sensors. The ARS is not designed to replace a manual micro-wind turbine switch at the site, but instead works strategically within the same wire run, giving the end users a safe and effective control strategy when at the site or when half a world away. Also, this product is proudly made in the USA. We hope this information on the new MCET-ARS has been helpful. For more information on the MCET-ARS remote control switch, FlexSCADA off-grid monitoring and control systems, wind sensors, or our line of super wind turbines, please visit us online at missioncriticalenergy.com. And as always, thank you for your time and attention with Mission Critical Energy.